Ladies and gentlemen, so we're going to be talking about adenosine triphosphate, or otherwise known as ATP. We're going to use this to segue into our understanding of the mitochondria and the process of cellular respiration. This is content that we've already covered in class, but for the benefit of those of you unable to attend, or for anyone that needs to rewatch the information and have the opportunity to pause it to kind of keep up with the content that we're covering, you can check your notes while we go through this, or use it to complete your notes. So we're going to start with ATP, and hopefully you'll find this video useful. I'm going to try to do it in a couple of parts. We'll start with our molecule here, and then we'll move into a diagram of the mitochondria that you have in your notes as well. That we're going to work through the process starting at the end and working our way to the beginning. Now, the goal of cellular respiration and the mitochondria is to create ATP. Now, as we've already discussed, ATP is the currency of cells. It's not the only form of energy that cells can use, but it is the preferred method for energy within the cell for any of the organelles and the processes that they are working through. Without ATP, your cells cannot function. Since you're made of cells, obviously, if your cells are not functioning, you do not function, which ultimately means you die. So the process of creating ATP is a very important one. To understand why this is a unique molecule, we're going to look at each of the individual parts that make it up, and then use this as kind of a springboard into cellular respiration. So to start off, here is our molecule of ATP, which stands for adenosine triphosphate. This section here of our molecule, we're made of three different sections here. This one here is known as adenine. Here we have a carbohydrate known as ribose. And hopefully you recognize this as a carbohydrate based on its shape and the elements that are part of it from our biomolecules lesson at the beginning of the year. Together, the two of these are going to form adenosine. So the combination of adenine and ribose is adenosine, which is where we get our adenosine from adenosine triphosphate, which means here we have what we will refer to as our phosphate group. Now, phosphate is essentially just phosphorus with 4 oxygens. So in between each of these, we actually have 2 oxygens that are covalently bonded together, but I'm not drawing both of them. So just assume that they are each sharing electrons between 2 oxygen molecules to separate each of those phosphates. Now, triphosphate, tri prefix, tri meaning 3. So we have 3 separate phosphates that have bonded together to create our phosphate group. Now, a phosphate, as a chemical formula, and this will be useful later when we look at cellular respiration, is going to be PO4. And that's going to come up when we look at cellular respiration. So I just want to throw that in there as an aside. You can include that in yours as well, if you'd like to. Now, ATP as an energy source is very useful, very practical for the cells, but it's also very unstable. And the fact that it's unstable is one of the properties that makes it a valuable resource for cellular respiration, or at least for any process that cells are going to use. Now, the reason for its instability lies in the fact that it has these negative oxygens. Now, if you recall, when we talked about polarity, when we talked about charges for our subatomic particles, we know that like charges are going to repel. Opposite charges will attract, like charges will repel. And so we have a molecule that the phosphate group is made up of negative charges, but still bonded together. So we have this bond holding our phosphates together that are trying to actively push each other away. This makes it unstable. Now, the benefit of using an unstable energy source is that it does not require a lot of energy to break the bonds holding these molecules together. Keep in mind, we get energy from a chemical reaction by breaking the bonds that hold the atoms together, right? So we have these covalent bonds that are holding these phosphates together, and the covalent bond force is stronger than the repelling force of those phosphates. Those negative charges trying to push each other away are kind of being held in place by these covalent bonds. However, because they're already trying to push each other away, we don't have to add a lot of energy to break the bond to release a lot of energy. So this is a good energy source, even though it's unstable, because it doesn't take a lot of energy to get a lot of energy. And if we're trying to use an energy source, we don't want to have to spend more than we're going to get from it, which is why this is very practical and very useful for our cells. It doesn't take a lot of energy to break the bond holding our phosphate together, and it gives us a lot of energy in return, which is what makes this the preferred method of obtaining energy for cells and all of their functions. Now, ATP is going to be synthesized in the mitochondria. So we need to kind of zoom in on the mitochondria and look at that process. And we're going to start from the end and work our way to the beginning, because I think it makes a little bit more logical sense as to why these processes occur and how this plays a part. All right, so we're going to pause it right here for a second, and I'm going to add our new diagram of the mitochondria up here for us.